So the blue line shows the expected behavior based on the visible mass. And like the solar system, the speed should drop off dramatically once the orbit is outside the bulk of the mass, right? So, but the controversy that happened here on the velocity versus time curve was the velocity did not drop, it just stayed flat.
ओनली
Okay.
ऊपर
It sort of
इसमें भी
stayed more or less on a flat manner, or even flat, or let's say in this,
डिटेल्स डालना
according to this
पड़ेगा
image, which this graph, which is very similar for most of the galaxies, uh, either stayed flat or slightly increased far out into the galactic, the suburban galactic paths. So this is a massive violation of Newtonian gravity, um, which was predicted for visible matter alone. So for the velocity to remain flat, the amount of mass that is enclosed within that orbit must keep increasing linearly as the distance increases. I hope you agree with this. I'll repeat the statement again. So, if the velocity has to remain flat, or let's say in this case, slightly increased, the amount of mass that is sort of enclosed within the orbit should also increase linearly as the distance increases. And this should happen long after the stars have faded away. But this has been observed as a contrary, and we have a lot of research papers available on these, and we have a lot of research like controversies, conspiracy theories, and a lot of people who do not accept this variation in the observed graph,
थैंक
who give their own reasoning for that. All these are pretty much available. So if you would like to know more about those, you can let me know. I can send out some articles on that matter as well. But Vera Rubin's theory was one of the most leading ones, because she had imbibed it from Fritz Zwicky, which had clearly
इन
stated a
आउट
lot about inner circles and
इन
outer circles of galaxies, and how velocity
अंदर
and the time, or the radius, will be intertwined and codependent on these factors. All right, so there is a little YouTube video here. I can maybe, yeah, I will post that link, or do we have time? Yeah, I think we do have time. I can probably just show it to you quickly. That should be good. So I'll just stop sharing this screen and switch to YouTube. You can let me know if the audio is, you're able to hear the audio. Also share tab audio, yes. Okay. You should be able to hear the audio.
Hello, welcome to Astronaut. Today we're talking briefly about galaxy rotation curves, a graph that indicates the existence of dark matter.
I feel like an astronaut in the, what you know about rolling down in the deep.
A galaxy's rotation curve showcases the relationship between the velocity and radial distance from the center of the galaxy. What would we expect this relationship to look like? According to Newtonian mechanics, v, the velocity, is equal to the square root of gm over r. This comes from equating centripetal force to gravitational force. mv squared over r, the centripetal force, is equal to the gravitational force gmm over r squared, where m represents mass and r represents distance. At the very center of the galaxy, there is no mass, so the velocity is zero. In the inner part of the galaxy, as the distance from the center increases, the mass increases, and thus the velocity increases as well. After a certain distance, which we often measure in kiloparsecs, the mass of the stars in the galaxy does not change significantly. At this point, as the distance from the center of the galaxy increases, we expect the velocity to decrease. Observations, however, reveal that the velocity remains relatively constant across multiple radii. Since g is constant, we assume an invisible mass is compensating for the disparity in velocities between what is expected and what is observed. A rotation curve is often calculated from observations of hydrogen, so rotation curves only extend out as far as there is neutral hydrogen. Most galaxies have dark matter, but it is suspected that not all galaxies do. Some observations suggest the presence of galaxies that only have visible matter. Okay, well, that's pretty much all for today, so thanks for watching, and as always, ponder, wonder, and go right in the stars.
Right. Um, I hope you've um, I hope you've got some idea about how the rotational curves work. Can someone please confirm?
Yes, ma'am.
All right. Okay, so it's a very simple topic, basically. If we were to run in a smaller circle, we would run faster. If we were to run in a bigger circle, we would run slower. If we take up the same speed. Now, we can't assume that it takes up the same speed here. I mean, we can't assume that it is taking up a higher speed here as it goes into a bigger circle. So the only other explanation is that there has to be an invisible mass that is fueling this. Now, that mass is what has later come to be known as a dark matter. Hope that's clear. All right. Okay, coming back to our topic. So that was a little something I wanted to cover, which I couldn't cover with the graph last session. So, all right. I think we'll go back to our. Yep. Okay. Hope that is clear. And so today we'll be starting with our active galactic nuclei and cosmic structures. Here in this session, we'll be looking into some central engine topics like SBH, that is supermassive black holes. It's called SBH or SMBH. Excuse me. And the stellar orbits around Sagittarius A star. Someone had mentioned about Sagittarius A star last session. I don't recollect who. But Sagittarius A star, can someone tell me what Sagittarius A star is?
Mobile number?
I guess it's a black hole.
It is a black hole, but we should be able
Mobile
to
number?
recognize it in a better manner.
It's the black hole at the center of our galaxy.
Yes.
Exactly. So this is the massive black hole in the middle of Milky Way. Right. So yeah, that is about Sagittarius A star. Then we'll be looking into AGN power. Is anyone familiar with the
Gadi
term
number?
AGN?
Okay. 05. Yeah.
No, ma'am.
It's sort of an abbreviation for a bigger term.
0117.
Okay, it's called active galactic nuclei. Does anyone know anything about AGNs, or is there any knowledge of yours that you would like to share before we start AGN?
Yeah, the centers of the galaxy are very luminous and high energy, and the output of the center black hole itself is stronger than the entire galaxy.
Okay. All right. Okay, that's a good input we have. We'll start from there. Yeah. And we'll be looking into a unification view wherein we'll be explaining about the AGN types, how they occur, why they occur, how to observe them, etc. And cosmic architecture, wherein we'll be talking about the hierarchical, the formations and galaxy clusters. And we'll be looking into the regulation part of it. So let's move into the first topic of central engine. All right. Okay. Yeah. So, coming to central engine, we have something called supermassive black holes, which is otherwise called SPH or SMBH. So, let's first off try to establish the existence of SMBH, right? So, how do we know there's a supermassive black hole at the center of our own galaxy, which is the Milky Way? How do we know that? Do we have any proofs? Have you read about anything of that sort?
হ্যাঁ এরকম চলছে চলে যায় কোনোরকম
Guys, come on, give some answers. If you don't know, please feel free to just say you don't know.
Can you repeat the question?
Yeah, so I was asking, how do we know that there is a supermassive black hole in our galaxy if we know that there is or there isn't? How can we be sure?
So basically, what I believe, what I've read some time ago, that
Hmm.
there are some stars or some heavenly bodies that are orbiting something in the center of the center of a galaxy, and we were not sure what they were exactly orbiting. So based on the data, that many things are orbiting some dark thing in the center of the galaxy. So after that, we got an idea that it must be a black hole. It has to be a black hole because
Right.
there was nothing else visible there. Because I don't think that
Oh,
Sagittarius A is. I mean, the black hole can only be identified if the surrounding areas are
of
being
course.
affected. So
Yeah.
something like this was happening, I believe.
So you're basing it on the light that is not, we are not able to get a light from that area, so definitely it has to be a dark area. Is that what you're saying?
Yeah, I mean, I am not basing it on the light per se. I'm basing it on the heavenly bodies that
Hmm?
must be orbiting around some dark thing in the center of the galaxy. There were some planets, or I mean, I don't know what, but what I remember reading, that there were some planets or some bodies that were orbiting the center of the galaxy, but we were not able to identify what exactly they were orbiting. But there was some heavy mass, dense
Okay.
something. So I guess
So
that
it's about the orbital path that you're
gravitation,
basing it on.
due to the gravitation force, yes.
Okay. Okay. That's actually almost the point, actually. Thank you. I'm not sure who just spoke, but
Myth.
Nimit, all right. Thank you so much, Nimit. All right. So, yeah. So this question has been there since the time someone came up with the term black holes. We wanted to always know whether there was one in our own galaxy. So the crucial evidence to this comes from tracking the stellar orbits, obviously, as Nimit has mentioned. Uh, it's about tracking the orbits of the stars, and this has come up with from Sagittarius A star, that is the Milky Way's black hole. For decades, actually, astronomers have used some infrared telescopes to track the motion of some specific stars. Like we have stars called S2, SO, then SO1 or 2. SO 84, all those specific stars were tracked by their motion, and these seemed to orbit incredibly close to the galactic center, right? So these were like more or less around the center of the galaxy, and these stars were orbiting an invisible object at very high speeds. At very high speeds, like for example, there was a star called S2. The S2 completes a full orbit in only in just 16 years, wherein it took like a normal star would take around like millions of light years, or at least hundreds of light years. But this was just completing it in just 16 Earth years, right? Just 16 years, so that is incredibly fast. So this would give up give us sort of a speed where it was 5,000 kilo sorry, 5,000 kilometers per second. So we wouldn't probably be able to imagine that sort of speed. But 5,000 kilometers per second was the traveling speed of the stars that was orbiting closer to the galactic center. So using this, when astronomers have applied the Kepler's third law, now can someone tell me what Kepler's third law is? I think we have already taken those.
I believe that the square of the area. No, no, no. Sorry, the
Square of the
Yeah.
time.
traversed by a body around.
Square of time period is proportional to cube of distance.
Hmm. Okay. Do you want to quickly check Google and tell me the exact wordings of those? The formula you've told is more or less the same. Yes. Come on. Get it up soon. Someone please shoot.
Ma'am, do we have to say the definition?
Yeah, sure. The third law. However, you are able to put it in a way that everyone can understand.
Okay, I mean, I don't remember it, but by what Google says is the square of the orbital period of a planet is directly proportional to the cube of the semi-major axis of its orbit.
All right. So how would you like to explain that for everyone's understanding here?
I mean, if the orbit is in an elliptical shape, there will be a two foci or the axis. So, and the or stellar object in which the sun is generally placed, it is in either one of the foci. So, depending on that distance, the that is the major semi-major axis which is taken, and that is directly proportional. The cube of semi-major axis is directly proportional to uh, the total orbital period or general time taken, the time square
Yeah,
or the
okay.
revolution.
So in simple words, if you have an ellipse and two two foci, and in these two foci, one of the foci will have the star. So whatever is orbiting will be completing the full ellipse. When it comes closer to the star, what happens? Is it faster or slow?
Fast.
Fast. And then when it goes farther,
It slows down.
sorry, yeah, it's the other way around actually. It goes faster on the outer and slower when it comes to the near the star.
Okay.
Yeah. So that's how it completes the rotation. So the same third law has been applied here, Kepler's third law, and the orbital mechanics demanded that the sort of central object must have at least the mass of 4 million solar masses. And this massive, extremely massive star should fit within a region that is smaller than the orbit of a small planet, like, for example, Mercury. Um, and it was confined in this smaller space with a lot of mass. So this had explained a lot of factors about the SMBH. And since no combination of stars or gas or dust could be that dense and that massive without creating some sort of radiation outwards, it must be a black hole. So this was the entire sort of conclusion that they had brought up when they were in the question of whether our galaxy has a supermassive black hole or not. So it was the massivity, and it was the kind of radiation that could have been emitted if it was that massive within just that much of a region. So this couldn't be possible. And then, if this is not possible, then it definitely has to be some sort of empty space or a dark space where radiation, the light, none of those could escape or go into. So that has to be a black hole. So this was the conclusion. And beyond our galaxy, we see a sort of universal connection, and this connection is called the M sigma relation. And this M sigma relation is basically a very powerful empirical result showing that the mass of an SMBH, or a supermassive black hole, is directly proportional to the random motion of the stars. And this random motion of the stars, which are in the host galaxy's central bulge. Hope that's clear. I'll repeat that again. So the M sigma relation is nothing but there's a relation between the mass of the supermassive black hole and the motion of the stars. So it says the mass of the supermassive black hole is directly proportional, as in it has a direct relation to the random motion of the stars in its host galaxy's central bulge. So whatever stars are at the central bulge of the galaxies, we had seen the other day about a central bulge and like a bright spot in the middle. So whatever stars are orbiting in the central bulge, and their random motion is directly proportional to the mass of the supermassive black hole. So this tight correlation suggested that the black hole was not just a passive sort of, just sort of a matter that is existing, but its growth is sort of coupled to the formation and growth of the galaxy in itself. So if the black hole expands, then that means the stars around it has a random motion that is expanded. The galaxy in itself is expanding. So this will also indicate that there are like evolution of billions of stars every year, or probably every moment, that even right when we are here in the session, there could be evolutions of stars that's taking place. So all these are correlated to the massivity of the SMBH, as the name suggests. So that is about supermassive black holes. Hope you've got some idea about it and how evident it is, or what does it correlate to. And M sigma relation is also the kind of topics that is, being researched on actively right now. Uh, I personally know a few PhD students who are doing their thesis on M sigma relations. So it is a research that is actively rising, and there'd always be new things to learn about M sigma relations. Yeah. So now we are getting into the active galactic nuclei power, or the AGN, right? So we'll quickly get into that. So so where we stopped saying in the previous section was the black hole in
খাওয়া
itself
পরে
is extremely dark. So where does all the energy come from?
এই ছোট্ট একটা জব ওইটাই করছিলাম, ওটাই আর কালকে হবে।
Does someone want to put in your thoughts here?
ভাত, দুটো
from the
রুটি,
accretion disk.
ভাত, সাম্বার।
Exactly. So yes, the accretion disks, and we had learned about a few disks other than the accretion disk,
ওকে রুটি,
or
ভাত,
another
সাম্বার,
names of
ডাল,
accretion disks around the black holes.
একটা
Can someone tell me the terms that started, that the
রাখবে
terms that
17
we named for the accretion disk around the black holes, up to which point the light would reflect back?
Event horizon.
Yes, event horizon, yes. I think there was one more term associated to the same accretion disk.
Yes, there was.
Mhm.
I don't remember that.
All right. Okay, no problem. All right. So event horizon is the main, and the other term, please find it out. I'm not going to say or explain it right now because you will have the minor project primarily based around those topics. So you will have to go through. Probably you will have to go through the recordings once again, once or twice again, to brush up your topics maybe. So you can check those out at that time. Anyway, so yeah, the event horizon is the major one. So event horizon is up to which the light can reflect back. And so these accretion disk is where all the energy for the black holes come from. And this disk is sort of the most efficient, you can call it the engine of the universe. And the entire universe, or the entire galaxy for that matter, or whatever the black holes, whatever energy that's coming from the accretion disk um, out of the black hole is probably propelling the whole of the universe, or at least the galaxy in itself. And this very efficient engine of the universe called accretion disk, or the energy that's coming from the accretion disk, is converting a lot of gravitational potential energy into light. And basically, as gas loses some angular momentum, uh, and once it loses angular momentum, what happens? It'll just form a helical, or it'll just spiral towards the inside. And once it spirals towards the inside, it'll accelerate, and there's a lot of tremendous internal friction that is happening due to this high speed spiraling inside. And that friction, or you can call it in the internal friction, is also termed as viscosity when it comes to astrophysics. Well, in other branches of physics, viscosity has tentatively has a different meaning, or different conceptual idea about it. But here, for internal frictions, we for this particular, at least, we use viscosity. Even in the other branches of physics, we call the internal friction viscosity, but mostly associated to liquids or fluids. But here, yeah, we talk about the internal friction when it comes to spiraling gases, and some angular momentum loss and helical downfall. All of that is called the viscosity. And this internal friction, or the viscosity, will start heating the core plasma. And so what happens is the inner disk will become incredibly hot because of the spiral and the internal friction increasing. So obviously, when there is a friction increasing, when there's a lot of friction, there is heat produced. Like, even if you just rub your hands or your palms with each other, after a while you'll start feeling a sort of heat. So any sort of friction will produce a lot of heat, and in this case it is high speed and spiraling inwards, and all this heat is projected inwards. And this heat that is produced are probably millions to billions of degrees, and they are radiating intensely across the entire EM spectrum, or electromagnetic spectrum. And that is in the form of radio waves, even powerful X-rays, etc. So crucially, the efficiency of this engine is sort of staggering because of the spiraling inwards. It's just losing a lot of its, you know, efficiency part of the engine. It's losing a lot of it. So in a star, basically, a nuclear fusion converts around um, less than 1% of its mass into energy when there's a fusion taking place, right? But on the other hand, the gravitational energy that is released by the matter falling into the spinning black hole will convert up to 40% of the mass into energy. So you can imagine how much of an energy is produced from a stellar fusion, or and how much of energy is produced by just spiraling, by just the the gases, etc., just spiraling into the black hole. So if in the stellar fusion it converts only about 1%, and that 1% is lighting up an entire world or entire solar system, and just imagine if it's 40%, how much would it be bright, and how much radiations could be sent out, how much light is produced, or how much energy is produced there. So this is why a quasar is the most powerful type of AGN, or active galactic nuclei. So this is why a quasar can be sort of hundreds of times more brighter than its entire host galaxy. So an entire galaxy could be lit up, plus it could be more brighter than an entire galaxy, that the star or the quasar in itself is more brighter. Uh, I think the term quasar has been associated to the brightest that we have heard. So this is the reason behind it. This is the physics behind it. And this power, however, has some sort of critical limit, right? So everything comes with a downside. So there is a critical limit to this power, and that critical limit is called the Eddington limit, or ELED. So Eddington limit is nothing but, as the disk's luminosity increases, okay, as the accretion disk's luminosity increases, the outward pressure from its own radiation will start to push the gas away from the black hole. And when this outward radiation pressure balances the kind of inward gravitational pull, the accretion flow will stop. And this accretion flow stopping can stop a lot of energy incoming to stop as well, and that is called the Eddington limit. I'll just repeat it one more time. I'm sure it must have just gone like that. Anyway, so Eddington limit is sort of a limit that will stop or like slow down the kind of energy that is just scattered out of this process. So basically, we have the accretion disk, okay, and the accretion disk's luminosity keep increasing over time because of the internal friction that is taking place and the heat that is produced. So when the accretion disk's luminosity keeps increasing, there is an outward pressure from the accretion disk, or from its own radiation, that will start to push the gases away from the black hole. And when this outward pressure that is pushing the radiation outwards, when this outward radiation pressure is sort of balanced by the inward gravitational pull. So I've always mentioned that whatever is coming out from the core of something in the outer space, it's always crushed inside by the gravitational force. So that is how most of our explosions happen in the outer space. Whatever is trying to push out from inside is being crushed from outside into the core by the gravitational force. So similarly, here also we have the outward pressure that is being pushed out, and we have the gravitational pull that is just gravitational push that is pushing it inside. So in when the gravitational push is sort of balanced by the inward force, then that will stop the accretion from flowing. Hope that's clear. So in this case, a quasar, essentially, which is a supermassive black hole that is accreting at this maximum, or at least close to maximum rate. And this extreme activity is usually why quasars are very commonly or predominantly found in the early universe, when the galaxies were, filled and flushed with gases. So this is about quasars and how quasar powers are extremely high than the stellar fusion, and how there is always a downfall, whereas there is always a limit put to that as well. called the Eddington limit. Hope that's clear.
Yes, ma'am.
All right. So now we are moving into something called the Aegean unification model. So, hope, give me a moment. My screen is sort of stuck. Oh, I'll just stop presenting and come back, please. My screen is stuck. I'm not able to move anything. I- Okay. Okay, I'll just try sharing one more time. Please just let me know if you're able to see my cursor moving. Got it. Can you see my cursor moving by any chance?
Yes, ma'am.
Okay. All right. All right. Cool. Okay. So, all right. So basically, the Aegean unification model has a lot of sheer variety to Aegean. That was basically a big puzzle, and Aegean in itself was a bigger puzzle that a lot of people had found really what do you say, confusing about how to uh, dissect it and learn more about it in depth. But we have a sort of unification model that has brought together a lot of a lot of things at the same time and has given us sort of a geometric idea to it that can explain a lot. So we should understand that the Aegean model or the Aegean in itself is all about the viewing angle. So they're all the same engine, but a crucial element here is the torus that will determine what we see. So the torus is the key component, as you can see on the slide. So the torus is nothing but a very thick, opaque, sort of donut-shaped collection of dust and molecular gases surrounding the black hole's accretion disk. Now, it acts sort of as a shield. Now, if our line of sight passes through the torus, we can't see the bright core. If we look above or below it, we can. So I have an image in the upcoming slide. We'll be able to understand a little more there. So once again, I'm just mentioning it once again for you all. So as we know, torus is sort of a donut-shaped ring, and it acts a sort of shield. And if our line of sight, it all depends on our line of sight. And if our line of sight passes through the torus, as in through the middle of the torus, we can't see the bright core. But if we look below or above the torus, we should be able to see it. Now, if we view the system at an intermediate angle, like if we have a direct line of sight to the accretion disk, then we can classify this as a quasar, or I think this table should be more useful here. Yeah. So I've just put on the viewing angle and what you can observe at this at which point. Yeah. Um, okay. So if we have a direct line of sight, I mean, if we have to classify this as a quasar or a type one, yeah, so we already discussed about blazars. So that is when we have a direct line of sight. And if we have to classify as a quasar or a type 1 Seyfert, so Seyfert is another term for the kind of quasars that we see based on the brightness of it. So if we have a quasar or a type 1 Seyfert, they are extremely bright and their light kind of shows broad emission lines because we see gases moving very rapidly toward and away from us. So due to the transmission of gases, we should be able to see very loud, broad emission lines. Now, if we view the system edge on, like, how can I show it here? Okay, yeah, okay, so this one, the edge on. So if we view the entire torus's edge, or if you have a larger angle from the sides of it, then the torus will completely block the core, because obviously if you have the sort of what do you say, like a semicircular donut like thing, and if this is the circle part of the donut and there is a hole here, and if you look at it like this, you won't be able to see the middle part of it, obviously, because you're seeing the sides of it. You won't have a direct vision to the core of it. So torus will completely block down the core, and we can't see the bright disk, and we'll only see sort of a faint reflected light, and this appears as we can see here as a radio galaxy or a type 2 Seyfert. And finally, yeah, finally we have a polon angle. A polon angle is when we are directly looking down the barrel. Like, let's say this is the donut and we are looking down at the into the hole, as in we are at the pole and we are looking towards inside the torus. In that case, it is a barrel of a sort of relativistic jets that's happening there. And the jet plasma that is moving sort of nearly the speed of light, it is dramatically brightened, and it is just brightened drastically. And this is because of some Doppler effect of boosting. And because of our line of sight, since we are looking from here, all we see is light around us. It's all light everywhere. So what we can see is sort of an apparent visual, or the Doppler visual. Now, this creates a sort of highly variable and sort of an intense object called blazars. And this unification model has transformed the entire the field based on blazars and quasar, type 1 Seyfert, and radio galaxies, type 2 Seyfert, all of that. So in the upcoming slide, I'll just show you. Yeah, so here, if you want to check, this is a quick definition of relativistic jets that I've given. These are nothing but very high velocity beams of plasma that is launched from the poles of the magnetic fields responsible for powerful radio galaxies. So this is this is especially interfering with our line of sight when we look from the poles, because when we look from the poles, it's all relativistic jets around us. So all we can see are the jets and the apparent occurrence of blazars. Right, so I'll just show you. This is torus for you guys. So as you can see, this is like the side section of it's sort of a cross section of the donut like structure. So it is cut here just so you can see the core. So here the relativistic jets are going from here pole to pole, and we have point of view edge on. The edge on is through the side, and we have from the pole is here. If you have an angular or intermediate, it's somewhere from here. So with this image, you can once again check. Okay, so pole on is nothing but from the top. Okay, so if you're standing here and looking inwards, you will obviously feel like all the relativistic jets, you're standing in the middle of the relativistic jet path and you're looking inwards. So you will be seeing the core directly, but the brightness would be varied. Now that is blazars, and intermediate angle is somewhere from here, wherein you're partially covered up, and yeah, the accretion disk could be visible inside here. And edge on is nothing but this one from the side, so you can't see the core at all. So that is about the unification model, wherein with one table and one image, we are able to understand a lot. I mean, this is not exactly like, this donut shaped structure is not exactly there. It is an imaginative way of putting it so that you can imagine how the core works, how the line of sight works, and how the whole structure may or may not be. Right. So this is the most understandable way of putting an AGN function together. Hope that's clear. And today, now we are going to the final section of our today's session. That is the cosmic architecture and regulation. Do we have any doubts up till now?
No. I have a doubt, but I'll ask it in the end.
All right. Sure, sure, sure. That's up to you. All right. Is it based on AGN or is it based on the topic before that?
It is based on the efficiency and also related to somewhat related to AGN.
Okay, cool. All right, no problem. We'll check it at the end if you're comfortable with that. Meanwhile, I forgot a very popular tradition we have, wherein we have to click a snip of the session. All right, guys, say cheese. All right. Thanks, everyone. I'll just save that up. And we'll go into our final section. Okay, so all right, so we are at the final section of our galactic topics, and this will be dealing with cosmic architecture and regulation. And we'll see how the cosmic architecture works. It's more like the hierarchy, and the regulation is more like a feedback system. So, yeah. So the evidence for dark matter and oh, okay. Okay, sorry. I did not change the title of the slide. I'm sorry. So this is about cosmic architecture, guys. Please don't mind the title. I'll edit it up later. I'll just edit it up now. I'm sorry. When I just duplicated the slide, it sort of got repeated. Okay, I'll just. Oh, by the way, I've seen a lot of mismatches in the SS Signi project that you've all done. If you have any trouble finding the sort of plotting, or if you're not able to find the sort of graphs that I was asking for, or the spectral the spectrums that you have any trouble finding, and please reach out uh, for this project, that whatever you've put is considered. But as we go, if you would like any more sort of inputs wherein you're not able to find the sort of spectral emission lines, or if you're not able to find the sort of graphs that I've asked you to find, please let me know. So I can provide some sort of source for that, which will make things easier as well. So yeah, I have to let you all know about that. Okay, I'm gonna share now. And I'm really sorry, guys. A lot of edits are coming in between because these are all last minute presentations that I'm setting up after coming back from work. So thank you very much for understanding. I think I didn't present yet. Okay. I hope the screen is shared now.
Yes, ma'am.
Yeah, okay. Yeah, so this was the slide. All right. Okay. So yeah, so we have come down to the galaxy clusters and the hierarchical structure, wherein we'll be discussing mainly about the hierarchical structure formation, as well as something called an ICM, which we'll be looking into in the upcoming slide. So basically, we have the galaxy clusters, and uh, basically a collection of a lot of galaxies, like could be ranging to thousands of galaxies, right? The theory of this structural formation um, sort of is in what the universe is built in itself, and from the bottom up. And the dark matter that we discussed about in the previous session sort of collapsed into the clumpy form that we could be able to identify, or we could be able to study in detail. And this dark matter that is collapsed into certain smaller clumps, um, and later these clumps collected stars to form galaxies, and these galaxies sort of merged over to form larger structures. And this is the sort of formation of galaxies that we have learned in our previous when we discussed about the formation of galaxies and so on. So this is how I'm just mentioning it as bottom up, because it starts from very tiny gas and dust particles, and then goes on to accumulate the accretion disk. It escapes, scatters small proto stars, and then it again accumulates, and one star combines with another star, and there is little galaxy formations which just adds on as it goes. So the hierarchical, or the structural formation of galaxies are very familiar to us from our previous sessions on the galaxy formations. Now, one important thing that we need to keep in mind is something called an ICM, or as you can see here, it's the intra-cluster medium. So So intra-cluster medium, as the name suggests, it's intra-cluster, or it is within the cluster. Right. So the space within a sort of cluster is not empty, and it's sort of filled with some contents called intra-cluster medium that can have, like, what do you say? It could be a sort of a reservoir kind of environment of very diffused and hot plasma, and this plasma is heated to millions of degrees, and it's extremely hot plasma. And this heating mechanism is also very immense. That is, some gravitational forces from all the galaxies will come together or get coupled up with the shock waves that is produced, and this shock waves are coming from some mergers that took place very recently, or some very frequent, very recent, like the closest merger that they had, and that's where all the shock waves, because a merger, obviously there is a collision involved in a merger. So when there's a collision involved, there's a lot of shock waves, and there's a lot of heat and energy escape that is taking place there. So all of these are utilized in, or you is a part of the ICM. And when these gravitational forces from the various galaxies are, put together with the shock waves and the heat and the energy that is coming from the mergers, it heats the gas to a point where where the heat sort of crosses a boundary and starts giving out only very powerful X-rays. And this X-ray sort of emits gas in very massive quantities, and these massive quantities would help us to sort of identify the sort of density and the massivity in those regions, and you can easily identify that, okay, so this area is extremely massive because of so and so composition. Again, that comes out of detection methods that we uh, will be discussing for our final project. And in a typical extremely large cluster, right? Like if the merger is high, and if there's a lot of shock waves produced, and if there's a lot of heat and light generated, then obviously the cluster is extremely high, or the ICM medium is very densely occupied. Then the hot gas of the ICM actually contains way more mass than all the stars in all of the clusters that is combined. So the massivity of the cluster alone, with all the stars' massivity in that case, would be very very highly comparable, because the cluster in itself will be extremely massive. Right. So, but one thing I would like to tell here is, as we had checked in part one, even this sort of a massive reservoir is only, let's say, only a second largest mass component. So the total cluster mass is still very overwhelming, and is dominated by some invisible, unknown, a balancing something called a dark matter. So dark matter is never really, you can't just name dark matter. Okay, you can't pick something and say, okay, this is dark matter. Dark matter is nothing but a lot of extra mass that something should have had to balance both the sides of the equation, or to keep both the sides of the equilibrium. So it just doesn't seem right. There has to be something extra that we are not able to, identify yet, to be able to balance both the sides. That is dark matter, right? And this dark matter, as we know, would provide the sort of gravitational potential to hold the entire structure together. Only then there is an equilibrium that we can weigh out. So this is the intracluster medium. And this is nothing but the medium that's formed within the galaxies to to overcome the sort of, the shock waves and all the merger impacts there. And this intracluster medium could be so powerful sometimes that this could have an itself of a massivity even more than all the stars put together of the cluster. So this is about intracluster medium, and we are coming to, okay, so I think I've given a sort of, yeah, so the total cluster mass is dominated by dark matter, that is 80%, and ICM, that is intracluster medium, for about 15%, and all the stars are 5%. So we had discussed in the previous session that around 15% was only what is visible to you about galaxies. The rest is the dark matter. So similarly, the 5% is stars and the 15% is ICM. So I have put this split up because I think someone else had mentioned about how much of these are stars. So I tried to find out the percentage accordingly. So the stars alone are just 5%. Whatever is bright to you, uh, what is brightening up visibly for an entire galaxy, all of that is just 5%. And there is a lot of intracluster material or intracluster matter that is going around, and that is 15%, and the rest entirely is just to balance the equilibrium. People have just put it as dark matter. So that is the sort of combination we have here. And coming to uh, the final part of our today's session, we have feedback, mergers, and conclusion. Okay, so here in this concept is basically about how the entire system is kept in equilibrium, or say in balance. So this entire system is kept in a sort of balance. System of galactic system is kept in balance due to AGN, that is nothing but active galactic nuclei, that is the core. Right. So in, let's say, a very massive galaxy cluster, the hot intracluster matter will try to cool down. As it cools down, obviously what happens when something tries to cool down from heat, there's a lot of precipitation happening, or like some sort of condensation, that or some sort of dewing up happening. So this precipitation, all the precipitation that is happening due to the cooling down of the ICM inside a galaxy, will flow right towards inside the central part of the galaxy. So all of that, all the intracluster matter trying to precipitate, all of that will just be pushed into the center. All the precipitation will be pushed down into the center part of the galaxy, and this what happens. So this is not anything hot that is coming to the center part of the galaxy, right? And for a core that is extremely heated up, and you have something cold coming up, what happens there? It'll There is a potential difference that is taking place, because to a hot surface, you have all the precipitation from cooling down is coming down. Obviously there is a lot of lacking of a lot, what do you say, all the energy production, heat production, all of these will start affecting. So in short, the fueling from the center of a galaxy will be impossible, right? And this will be sort of a runaway process of the star formation. And the universe should be having a lot of hypergiant galaxies to maintain, or to not get this situation affected. But as we know, we don't have a lot of hypergiant galaxies uh, in the universe, right? Now this will be sort of countered by, or answered by, the SMBH situation. So the supermassive black holes and the sort of jets that these supermassive black holes produce. So when the cooling gas falls towards the center, or when the precipitated coolants are falling into the center of a gravity or center of a galaxy, it'll activate a sort of black hole uh, due to this sort of potential differences that is happening there. And this black hole that is activated will turn into an AGN, or an active galactic nuclei. Now, the black hole that is like pre-turning into an AGN will release a lot of energy in the form of relativistic jets that I had mentioned earlier. So, relativistic jet is a very common uh, form of energy releasing in the outer space when it comes to energy being involved, and when there is heat and friction and sort of massivity that is involved, like in the outer space. Right, so it's always in the form of relativistic jets, mostly in the form of relativistic jets. And relativistic jets is, it has been so common that it's almost very easy to spot a sort of jet that is coming from a celestial body while we observe through a telescope. So we can look at the plots of where there is a hyperpigmentation, and how where the pigmentation is lower, and you can identify the sort of jets that is releasing from there. And this relativistic jets will act as sort of, because of this cool and hot situation going on, it'll act like a cosmic furnace, and it will violently reheat the surrounding gases. And these jets are enough to just bring back all the, the hot, cold, neutralizing situation into back to fire, back to heat. And this heating up of the surrounding gas will create a lot of bubbles and a lot of shock waves. And these shock waves will once again try to what? Will try to push those gases away from the central galaxy, and it'll effectively shut down all the cooling flow, and stop all the star formations, and bring it back to the hot center of the galaxy that it was. Now, obviously, there is a lot of gravitational potential forces that is being applied from the outside against these outward pressures. But again, these inward relativistic jets and all these the reheating of the center is way more stronger, and it'll push it out of the center. Now, this AGN feedback is very crucial. It is a very crucial regulatory mechanism for the universe. Now, this feedback will obviously keep the center of a galaxy heated up forever. Every time there is a sort of, what do you say, inward precipitation that is being pushed into the center, there is always the agent feedback that's acting, trying to bring all the relativistic jets to the middle, and just spread their army around, and just heat up the core once again, and push all the precipitation out. So that feedback, as in that regulatory motion, is very important for the heat stability of an entire system out there. Now, this will obviously link to, like sort of like a tiny, powerful engine at the center, right? The engine being the SMBH, or the supermassive black hole. And this will slowly count it to the final fate and the size of the entire galaxy, and the cluster environment, all of that. So, this is all we have to talk about the Asian feedback. So I'm sure we have more or less traveled from the microscopic motion of a density wave to the universe spanning power of dark matter and black hole engines. Um, so, to give you a quick summarization of both of our parts, right? Like we had a part one from last session and part two of today's session. Uh, we have classified the forms, and we have tried to solve the persistent spiral arms thing with the density waves. And we have tried to prove the existence of a non-luminous dark matter, uh, specifically the dark matter halo. And we have tried to explore the energy of AGN, quasars, blazars, all of these, and how it is visible through the torus. And we have learned about the feedbacks, the regulations in the center of the galaxies, and ultimately the final structure of the universe has been more or less gotten into an idea, I hope. So this is about it. This is the end of today's session. So if there's anyone who would like to um, just put out questions or have an interactive place here, please feel free. Someone had mentioned about a question that they would like to ask, right?
Yes, ma'am.
Yeah. Yes, Anuj, please go ahead.
So, ma'am, it was related to the efficiency,
Okay.
as in the accretion disks, it is said that it has the highest efficiency from mass to direct energy conversion, which is nearly
Mhm.
40%. So,
Right.
without attaining the C square, I mean, how is it
Yeah.
possible to even attain that 40%?
Um, yes, the 40% is able to be attained. I'm sorry, I didn't get your question. Are you asking me if the C square is attained or if the 40% can be attained?
Yes, I mean 40% is attained, but without gaining the c square speed. So how is
Uh-huh.
it possible to even achieve till 40%?
Ah, okay. So you're telling me
Or
about the
is it the
speed of
40% of the total mass related to conversion of energy? Only 40%. Is it that related?
no. So the light, so I believe your question is there is no light escaping from a black hole, then why or how would a C square be obtained? Is that
Yes.
what your question is?
Yes. Even in
That's
the accretion disk, I mean, how the
yeah.
mass is directly converted to energy.
All right. So the C square here, we take the light that is coming out of the event horizon.
Okay.
Okay.
Mhm.
Are you able to connect it there?
But the light, okay, the partial light, which the left of light, which is
Yes, exactly.
okay, okay,
So, yeah. And basically, when I say that this is a very efficient engine, what I mean is, okay, as I've mentioned, there is a spiral moving into the black hole, right? So when there is a spiral moving into the black hole with it losing its angular momentum, and it sort of this the spiraling inwards will accelerate even more, and there is a lot of internal friction that's taking place. So internal friction is providing most of the energy there. All right,
okay,
and the light is just picked up from the surroundings.
okay,
So, more than the light being taken into consideration here, it's the internal friction that is extremely terrific. That is creating up all the, that is creating a sort of a 40% energy here as opposed to the 1% in the nuclear fusion.
okay. So
Got
I
it?
mean, if considered, I can say that if there are 100 masses, so out of
Mhm.
100, 40 were converted to light or energy
Exactly.
directly. Okay,
Exactly.
okay, so it
That's a
can be
better way to put it.
related to the plasma.
Of course.
Okay.
Yeah.
And one more thing, as you said
About aging.
before, Not
Sorry.
exactly AGM. I mean,
Uh-huh.
related to AGM. I mean, you can relate it.
Okay.
You mentioned that black holes grow because the
Yes.
randomness, it increases the area of randomness. It is when balanced out, to be considering the mass of the black hole to the randomness,
Mhm.
to know what the total mass of the black hole or the SMPH will be. So
Yeah.
the randomness increases. So does that mean the black hole size is also increasing?
In a very negligible scale.
Okay.
Yeah. Black holes do expand. There are again lot of conspiracy theories on whether black holes expanding, and we must have all come across this part where universe is expanding, right?
Yes.
So in that also there is a side of people saying that this is black holes expanding are also one major part, and ultimately that the entire universe is going to be imploding into a black hole. So black hole is sort of like like captivating areas around it, but in fact more than captivating areas, I believe through what I have uh, studied, it's enlarging in a very negligible scale. Let's say over a billion or a trillion years later, it could considerably increase in size, but it could never be fatal, as in it could never be big enough to, because
Engulf the whole
as it
galaxy.
yes, as it expands in these negligible scales, the universe will continue to expand at a faster rate,
Okay.
right? So the a black hole increasing with the sort of energy that's like, let's consider the energy that is keeping the universe together, and the energy that is around a black hole, which could be obviously bigger.
The energy which is ruling, I mean, surrounding the universe.
The universe,
Yes.
obviously. So the universe is expanding at a faster rate. Compared to that, I think the black holes expanding is very negligible, and
Okay.
that energy will not be able to keep up with the energy of the universe. So even if it starts expanding, which I believe, yes, it is expanding, I'm not saying it's not expanding, but it's expanding, but at a very negligible rate. But universe expanding may or may not be a reason for this expansion.
Okay.
Yeah.
And one last question. It
Yeah,
is
please.
again related to black hole. So
Okay.
as the SMDH is being surrounded by the other stellar objects or the
Mm-hmm.
other solar systems. So
Mm-hmm.
the inner as we go inward to near to the black hole, the star systems which are available or there are already two the red giants or either on the verge of death or turning
Hmm.
into uh,
Yeah.
their other forms. So if one of them turns into a black hole and then it is
Hmm.
again revolving around the supermassive black hole, so
Yeah.
does it engulf or does it get added to the mass, or does it react in the opposite? Not it won't react as an opposite because of the negligibility
It
in
won't
front of.
deflect from each other. No.
Okay, but
Because
does it get
yeah.
added or will it react?
Yeah. So here, one thing we have to understand is black holes are something that is extremely dimensionless,
Hmm.
right? So if like okay, we have we have a bottle, okay, an empty bottle. You pour water into it, that water is being added into whatever was already in the bottle. That
Hmm.
is because it has a volume and it has a dimension. Now, black hole as it is, we should imagine as something that is non-countable, or it's extremely dimensionless. So whatever you add into it, there is nothing adding up there. So the
Okay.
term adding up in itself may not be the appropriate one to use there, but I'm not sure what else to use. But whatever that goes in black hole is not going to have an added mass or an added volume to it.
Okay. So
Okay.
the
So,
black hole,
so
the
to answer
supermassive
your
will
question,
engulf the smaller
it'll
one.
engulf, obviously, because
Okay.
it won't be repelling from each other because they don't have any opposing forces that will repel from each other. Obviously, there are some EM spectrums that's going around it, but once an implosion happens and once a star turns into a black hole, it is just um, an unrecorded space. It's an empty space, and that empty space just adding here, it's like a constant. Okay, so you must have in school or somewhere in college or in school, you must have learned wherein in some equations you add a constant for
Yes,
for
in
no
line
reason, right?
equations.
Yeah, so you add plus c, whatever you put with that, it'll just become plus c. So if you add 4 plus c, it'll, you can just rewrite it as c itself.
Yes.
Yeah, so the scene itself is just a sort of an empty space. It's a constant space. Whatever goes in, it's not adding anything up there, it's just there.
Okay.
Got it?
Yes, ma'am.
Now it gets really messed up when you know, when you start watching a lot of uh videos or researches, when you start reading about black holes, it's just not something our brains are developed enough to, you know, put into picture. So it's a different dimension altogether. So if you're planning on watching a lot more videos or research papers, do prepare your mind accordingly, because it can get really messed up when you try to understand a lot of these. But it's a very interesting field, and the fact that you're asking these questions are extremely wonderful. So please do check more on these. Yeah.
Yes, ma'am. Sure.
But try to be ready to look at it in a very different
Different
perspective.
perspective.
Yes, yeah, that's all I'd like to say. Is there any other question, Anuj?
No, ma'am, not now, but just a discussion related to. So we have a supermassive black hole in the center of our galaxy. So similar
Right.
way, there are multiple galaxies, billions to be precise. But each galaxies are also in a random state of moving, and
Mhm.
so even do they have the black hole or the supermassive black hole, depending on the galaxy size, do they also have the black hole at the center governing the whole process?
Well, you have told me the answer already in this question. Depending on its size, that's
Okay.
the answer.
And how does the each galaxy spin is determined depending on the galaxy black hole spin?
Yeah, the spins are depending on the EM field that it undergoes, and possibly by again, the size of the galaxies are a big matter. So if it's smaller, it could be spinning more faster. If it's bigger, it could be spinning more slower. And the size as well as the sort of you know, what all collisions, like there could be a lot of collisions that's taking place inside, right? What these collisions have, you know, scattered or given out, those will also play a major role in how these galaxies, how the center of these galaxies are, and how the composition of the galaxies are, how the spin of the galaxies are.
Okay. And since it is expected that the Andromeda galaxy is near in future to be colliding with ours, so
Mhm.
what catastrophic event it might lead to, and is there any simulation related prediction of how the both of the black holes will react?
Nothing. I will just show you an image and I'll tell you where we are and where Andromeda galaxy could be. So this is Milky Way, all right.
Yes.
Okay. One of these arms, I'm supposing it's this arm, is called the Orion arm. Okay.
Okay.
In the Orion arm, if you zoom in, zoom in, zoom in, zoom in, somewhere in this region, a tiny dot is Milky Way.
Okay.
And very close to it, another tiny dot is Andromeda galaxy.
Okay.
Okay.
Yes, ma'am.
And this sort of, what do you say? Um, these two colliding can't have a very, what do you say, it's not a heavy built in. Both of these, Andromeda as well as Milky Way galaxies, are not, they are just SBC, that is
Hmm.
extremely on the lower side of the, okay, if you see,
Bulge.
the most bulkiest kind of galaxies are somewhere here, okay,
Yes.
and we are somewhere here, both Andromeda as well as us. The merger, there's a collision going to happen, well and good, I guess, but the collision is not going to have a great impact on the rest of the system. And plus, this collision that people are really scared about is not going to happen in another uh, at least 100 million years. So we've got nothing to worry. But other than that, to answer your question, uh, if there is a collision happening, there is a very minute tremor in the entire system. The system is not going to be affected because of the massivity of our galaxies. Our galaxies are not very massive. As you
Okay.
can see, it's the SBC category, right? So it's not very massive. So the collision is not going to be something that's going to shake a lot of area. It's just going to be a very tiny earthquake sort of tremor. That's it.
Okay. Got it.
Now, that is the what do you say? For people living on Earth or within these systems, it could be something really huge. Okay, it could be affecting in a crazy way. But I'm saying, in the perspective of the entire universal system, this is not going to be a big deal.
Hmm.
Yeah. Any other questions?
No, ma'am.
All right. Thank you, Anuj. Anyone else who would like to have some fun discussions? All right, guys. If that's all, I think we'll call it a day.
Yes, ma'am. Sure.
All right. So take care, everyone, and good night. See you all in the next session, which I believe is on Wednesday. We'll have sessions on 2 consecutive days this week. We'll have on Wednesday and Thursday. We won't be having a session on Friday. So we'll be having it on Thursday. So it's on Wednesday and Thursday. So, guys, please gear up and please make sure you're all good to attend the session. And if there's any doubts, please feel free to connect with me, or there's always Google. So please keep researching, keep reading if you're interested. Please do that. All right, thank you everyone. That's about it from my end. If there's nothing from your end, we'll call it a day. Thank you. You may all leave.
Thank you, ma'am. Good night.
Thank you. Good night.
Thank you, ma'am.
Thank you.
నాకు చెప్పలే ఓ బిల్డింగ్ ఏంటి ఇలా ఫ్యూజ్ చెప్పింది ఇంట్లో ఉండేవాడు మామ పక్కన కొంచెం బాగా రావాలి అంటే ఎంపీ దాకా వెళ్ళిపోయారు టేక్ చేసుకుంటుంది అప్పుడు సాయంకాలం किधर चला है? आप जाएंगे ना, देखिए तो जितना आप जाएंगे ना आपका कौन है आपका गाड़ी नंबर मोबाइल नंबर P3D 789 दिखाइए गुडरिच का 7891 मोबाइल नंबर 9742414348 अच्छी कंपनी का ये बता दीजिए 9742414348 बढ़िया अच्छी कंपनी थोड़ा बता दीजिए किधर है ये यही पे है क्या अच्छे कंपनी अच्छा है हाँ अच्छा है थोड़ा मोबाइल दे सकते हैं तो आप मोबाइल हमारा रखते रहिए हम अपना मोबाइल दीजिए थोड़ा लोकेशन ट्रैक करिए क्या नहीं कोई बात नहीं एडजस्ट करेगा तो दीजिए अच्छे कंपनी को दे मैप दीजिए मोबाइल दीजिएगा तो मैप ट्रैक करें प्लीज किस कंपनी का है किस कंपनी का है कौन सा किस कंपनी का सुपरवाइजर है क्या नहीं गार्ड है तो इसलिए तो मांग रहा सुपरवाइजर हूँ मैं चेक कर रहे हैं अब बैठिए उधर अच्छी कंपनी लेकिन चेक करना है लेकिन गोदरेज में क्यों चेक